And so our galaxy will be left with just a whole lot of dying stars, sort of fading away. And these stars will fade away, the black holes in the galaxy will start to evaporate away, matter will decay, and eventually everything will kind of just fade out. There will be no structure left in the cosmos, and that's called the heat death. And that's a very sad story, but it seems to be the direction our universe is headed. There's a long time before that process is completed, but that seems to be where most physicists would say we're going. But it's not the only possibility, and there are some that are a little bit more exciting. So one of them is called the Big Rip, and this is one where dark energy gets a little bit more ambitious than what we think it probably is. So the way we think dark energy works right now is it actually comes from an idea of Einstein. The idea is that there's a bunch of stuff in the universe. Einstein was talking about stars. I'm going to talk about galaxies. Let's say you have a whole lot of galaxies in the universe, and they're all kind of pulling toward each other with gravity. Every one of these galaxies is experiencing gravity. And in a universe that's static, that's not expanding or collapsing, it's just stable, those galaxies should be pulling toward each other, and that should make everything kind of come together. And so when Einstein was looking at the evolution of the cosmos, he didn't know the universe was expanding, so he didn't see any reason why all of the stars shouldn't have already collapsed on themselves. So he had to come up with something to explain why there was structure out there in the cosmos that wasn't actively falling together, that was or hadn't already sort of collapsed. And so he put a term into his equation called the cosmological constant that could kind of counteract the gravity of all the stuff in the universe and keep the universe steady, in a steady state. So the cosmological constant is a term that you put into the equations of gravity that just kind of balances out the gravity of all of the matter and energy in the cosmos and sort of stretches out the space that those things are trying to compress. When it was found that the universe was actually expanding, you don't need the cosmological constant anymore because the initial kick of the Big Bang can keep things from having already collapsed on themselves. And so the gravity of everything would be slowing down the expansion, but it wouldn't necessarily mean that everything would have already collapsed. So if the cosmological constant is the dark energy, I should say, when it was discovered the universe was expanding, the cosmological constant was thrown away, but we brought it back when we found out the universe was accelerating its expansion, because now we did need something to counteract the gravity. We needed something that could make the universe expand faster, even though we had the Big Bang to start the expansion, that would not speed it up. So we had to have something in there that would not just counteract the pull of all the gravity, but actually speed up the expansion. And a cosmological constant can do that. So if we live in a universe with a cosmological constant, that leads to a heat death. It leads to, the dispersion of everything out of, the sort of diffusion of everything in the universe, because basically if you have a universe that's expanding, then the density of matter in it goes down over time because you have the same amount of matter, but a larger space. So the density, which is mass over volume, goes down over time as the universe expands. The density of radiation also goes down as the universe expands. But if dark energy is a cosmological constant, if it's just sort of a property of space, then when you have more space, you have more cosmological constant, and the density is just constant because it's related to the amount of space you have. And so you have more space, you have more cosmological constant. And so the density of the cosmological constant doesn't change. And so if you have matter and radiation trying to pull the universe together, cosmological constant trying to push it apart, then if the matter and radiation are diluting and getting less powerful, less able to do that slowing of the expansion over time, then eventually you're going to get to a point where the cosmological constant is winning, right? And then at that point, there's so little matter and radiation that it stops being important in the evolution of the cosmos, and you just have a universe that's on this runaway accelerated expansion. And that's where the heat death comes in. But you could have a kind of dark energy that's not a cosmological constant, that's actually something more powerful than a cosmological constant. You could have a kind of dark energy where the density of dark energy increases over time. And that's something called phantom dark energy. And if that's what dark energy is, then it doesn't just sort of move galaxies apart from each other the way that a cosmological constant does. It would actually be able to tear galaxies themselves apart. So it would become sort of more powerful within galaxies, within solar systems. And so you would first sort of tear galaxy clusters apart, and then you would tear stars off of galaxies. And then as the dark energy becomes more powerful, it would tear planets away from their stars, and then rip apart stars and planets themselves. And at some point, at a calculable time in the future, it would just basically tear space apart, destroy space entirely. And that would be known as the Big Rip. A few years ago, there was a paper about this, and NASA made an illustration of a little animation to illustrate what the Big Rip would look like, or sort of would look like. And I want to show this little video because I think it's a very nice illustration of this. So in this video, you see the expansion as normal, where the galaxies are getting farther apart, and then you see dark energy kind of ripping the galaxies asunder. And so that's how you end up with a Big Rip. And we don't know for sure if that could happen. Based on our understanding of the theory of how dark energy works, we think it's very unlikely that you would get this Big Rip happening, but we can't really rule it out based on the data. So we can do various measurements in the cosmos to try to put kind of limits on where we think where we think the universe is going. We can do various measurements of what we think dark energy is. And one of the measurements we do is of what's called the equation of state parameter, which is sort of the ratio between the pressure and the density of the stuff that's making the universe expand faster. And I won't go into the details of that, but if it's a cosmological constant, if the dark energy is just this constant property of space, then this equation of state parameter is just exactly equal to -1. If it's anything less than -1, then we have phantom dark energy that becomes more important over time. And so we can try and measure this equation of state parameter to see if we're going to head toward just a regular heat death or this Big Rip idea. And so when we use something like the Planck satellite, which is the one that's measuring that cosmic microwave background, to measure W, we get a number that's -1 to first approximation, but actually has room for being a little bit less. So the kind of best fit number that we get, the number that we first see when we do this measurement is a little bit less than -1, but we have some errors on that. So that plus or minus means that we could be off by that amount, which means it's consistent with exactly -1 with a perfect cosmological constant. The number could be a little less, a little more. So what we can do with that then is we can say, well, what's the most negative this number could be? So what's the range of possibilities? And if it's more negative, then that means that we have less time before a Big Rip might happen. So when we do that calculation, we can say, okay, we have at least about 188 billion years before the universe could possibly be ripped apart by phantom dark energy, if that's even a thing that can happen. And then we can actually go through and make a table of when various catastrophes in the cosmos would occur based on a Big Rip happening 188 billion years from now. So if that were to happen, if we really had that value of W, that kind of phantom dark energy, then 2 billion years before the end, galaxy clusters would be erased. 140 million years before the end, the Milky Way would be torn apart. 7 months before the end, the planets would be taken away from the solar system. Just an hour before the end, the Earth would explode. And then right at the end, you get atoms torn apart. This table, by the way, is based on a table from an actual scientific paper calculating these things, where they included this sort of timetable of doom in the results section of the paper. And I thought it was just a wonderful idea to actually spell out exactly when all these horrible things are going to happen to the cosmos. But again, probably it's not going to happen. If it were going to happen, we'd have at least 188 billion years, which brings us to another possibility for the end of the universe that is well, technically, it could happen at any moment. Now, when I say that, don't panic. I will explain why you shouldn't worry about vacuum decay, but I will say that we can't rule it out as something that could happen sooner, although it's extremely unlikely. So vacuum decay is an idea that's been around for quite a while, but has gained prominence in the last few years after the discovery of the Higgs boson at the Large Hadron Collider, which was sort of the last piece of the standard model of particle physics. Just to give a lightning overview of the standard model of particle physics, this is the set of particles we've ever detected or interacted with in any kind of experiment, including the Higgs boson, which was just detected in 2012. And so this mix of particles includes the quarks, which are particles that a few of the quarks make up the proton and the neutron that sit at the centers of atoms. There's the leptons, those are the green colored particles here. These are including the electron, which is the one that orbits around the centers of atoms, or if you want to think about it quantum mechanically, it sort of exists in this cloud of electronness probability around the centers of atoms. But it's this particle that's part of how atoms work. And then the neutrinos are also part of the lepton group. Then on the red particles there are the force carriers. So there's the photon. Photons are particles of light. They are what carry the electromagnetic force. They're responsible for electricity and magnetism. Then there's the gluon. That's responsible for the strong nuclear force that holds quarks and nucleons together in the centers of atoms. And then there's the W and Z bosons, which are responsible for the weak nuclear force, has to do with things like radioactivity. So when we measure the properties of these particles, it tells us something about sort of how particle physics works, the structure of particle physics. And by looking at the masses of a few of these particles, we can say whether or not particle physics in our universe is really stable or not. Based on, where by stable I mean not subject to potential disturbance that would change the way particle physics works. We don't want the way particle physics works to change because we are built of particle physics in the way that it works now. Our atoms rely on the laws of nature being what they are. We don't want those to change. So you can you can plot out different possibilities for what the mass of the Higgs boson might be, the mass of the top quark, and see where, you know, certain parts of this this kind of parameter space would give you a stable universe. Some parts would be in an arrangement of universe where it would have collapsed or destroyed itself already in some way. Some are very hard to calculate. You have the, you know, different possibilities for the combinations of these masses that give you different properties of the universe. Some universes, some sort of arrangements of these particles give you a stable universe where particle physics just works forever, and some where that's not the case. And so when we actually measure the properties of these particles, we find that we live right there. So that's in the region of metastability, which means that the universe is stable for now. And what it really means is that the Higgs field, which is this kind of energy field that pervades all of space, might be subject to changing its value. So the Higgs field is this energy field that has some value associated, some number associated with it. And that number kind of determines how particle physics works, determines what the mix of particles are, how they interact with each other, what their masses are. And it was different at the very beginning of the universe. The Higgs field had a different value, and at the very beginning of the universe, there were different sets of particles, and the way the forces of nature work together were different. And you couldn't have atoms and molecules and things at that time. And then the Higgs field changed, gave us the value it is today. Now everything's fine. We can have particles, you know, we can have atoms and molecules and so on. If the Higgs field value were to change again, that would change how physics works, and that would be bad for us. So you can kind of think of the idea of metastability as there are kind of two possibilities, or potentially more, but let's say two possibilities for what the Higgs field value might be. Okay, you can draw it sort of like this, where you have one possibility is this little valley over here, and the other possibility is this other valley in our our universe can be thought of like as a ball sitting in one of these little valleys, and if our universe sits in the higher of these two valleys, that's called a false vacuum, and then the lower one is called a true vacuum, because basically if you were to disturb the ball enough, it would land in the true vacuum and stay there. That's the more stable part. That's the more stable sort of region or value for this field to take. And so the idea is that our universe might be unstable in the same way that, like, if you take a glass and you balance it on the edge of a table, it's stable enough there, but it would really rather be on the floor, because that's like the lower energy state, the more stable state. And you don't want the glass to fall off the table, because that would destroy what was in the glass. And it's sort of the same with our universe. We don't want our universe to go into a true vacuum if there is one. So there are kind of two ways that the universe could transition to a true vacuum. One is if you disturb the Higgs field enough locally, if you found a way to interact with the Higgs field and disturbed it enough, then it could kind of go over that bump and end up in the true vacuum. Fortunately, the amount of energy that would take is far beyond what our colliders could do, far beyond what any future collider could do, far beyond of any process that happens in the cosmos. So we're pretty sure that can't happen. And when people panic about this with like particle colliders, just keep in mind that if our particle colliders could reach any kind of energy to really affect the Higgs field in that sort of way, then it would have happened billions and billions of times already in the universe, because the kinds of collisions of particles that happen in space are just many, many, many orders of magnitude higher energy than what our particle colliders can do. So nothing that we can do on Earth could actually affect this if the things in space haven't done it already. So we don't have to worry about that. But unfortunately, our universe is essentially quantum mechanical, which means that if you have a particle and a barrier, then it's possible that instead of having to go over that barrier, the particle could actually go right through the barrier. This is called quantum tunneling, and this happens all the time. We use it in electronics, we use it in certain kinds of microscopes. Quantum tunneling is just a fact of the universe, that sometimes things can move from one place to another without having to cross the distance. And that can apply to the Higgs field as well. So it's possible that some point in the Higgs field, a quantum tunneling event could occur, and the Higgs field there could tunnel to this other value. And if that happened, then it would create a little bubble of a kind of space that has a different Higgs value inside that space, where the laws of physics act differently and we are not able to survive inside that space. It's called a bubble of true vacuum. What that would look like is at some point in the universe, this bubble would form where this quantum tunneling event happens. This bubble would be then expanding out at the speed of light and destroying everything in its path. And because it's moving out at about the speed of light, if we are standing nearby, there's no way we can see it coming. So if that occurred, it would just destroy everything in its path. And at some point, there was a calculation of this in about 1980. There was some physicists calculating that this could happen, and they were further calculating that inside that bubble, not only are the laws of physics different and everything, so your particles can't hold together, but also the space in that bubble would itself be unstable. So anything that fell into the bubble would also then be crushed in a black hole, basically. They calculated that, and then they wrote a little paragraph about it. And I'm going to share that paragraph with you because I think it's one of the best pieces of physics poetry I've ever seen in an academic paper. So they've just